Welcome to For the Love of Physics. It's really great to have you with us today. A big hello to everyone listening from Ishik Boys High School, and especially to Mr. Jager's class. Get ready, because today we're doing a deep dive into something absolutely fundamental. We're going to explore the building blocks of, well, everything around you, and the hidden forces that make stuff behave the way it does. Why your desk is solid, why water flows, why the stars glow. We'll be digging into concepts straight from your physics textbook, hopefully making them click in a new way. Our mission today: to unpack this sort of silent language of particles, understand the push and pull that shapes our world. Okay, so let's start with something you see every single day: the different forms or phases that matter takes. You're probably familiar with solids, liquids, and gases. A solid, like your phone, keeps its shape and volume. A liquid, like water, keeps its volume, but takes the shape of whatever container it's in.
Right. Pour it from a bottle to a glass. The shape changes.
Exactly. And then there's gas, like the air we're breathing.
Yeah.
It doesn't have a fixed shape or volume. It just expands to fill the space.
Yeah.
But the really interesting question is why? Why is your phone solid? Why does water splash? It all comes down to the tiny bit of the molecules and atoms. In solids, they're packed super tightly, just vibrating in place. In liquids, they're still close, but they can, slide around each other.
More freedom.
Right. And in gases, they're way far apart, zooming all over the place. It's how they're arranged and how they move that defines the phase. But sometimes matter's a bit more, well, fuzzy, right? Take butter.
Yeah, a good example.
When it's cold, it's definitely solid.
Yeah.
But leave it out. It softens, gets spreadable, it's not quite solid, not quite liquid.
It's in between.
Exactly. It shows these phase boundaries aren't always super sharp. Things can change gradually depending on temperature and what the material's actually made of.
That's a really good point about the gradual change. So if a little heat changes butter that much, what happens if you go to really extreme conditions? Are there other states beyond the usual solid, liquid, gas?
Absolutely. And this is where it gets, well, kind of mind-blowing. There's a fourth phase of matter. It's called plasma.
Plasma. Okay.
And get this. Scientists estimate that plasma is the most common state of matter in the entire observable universe. By far.
Wow, really? More common than solids or liquids?
Way more common. Plasma happens at incredibly high temperatures, hot enough that atoms actually get torn apart. So you end up with this superheated, almost like a soup, of free-moving atomic nuclei and electrons just zipping around independently at crazy speeds. Think about the sun or any star. They're gigantic balls of super hot gas, right? But because the temperatures are so immense, the stuff inside isn't just gas anymore. It's plasma.
So stars are basically giant plasma balls.
Exactly. So when you look up at the night sky, you're seeing plasma everywhere. Estimates are something like 90% of all the normal matter we can see is in this super energetic plasma state. It's wild.
And thinking about changing phases, like ice melting to water, then boiling to steam, that really shows energy in action, doesn't it?
Totally.
You're adding energy, usually heat, so thermal energy, or sometimes changing pressure, and that energy makes the particles move differently, interact differently, and shift the whole phase. Matter isn't static, it's always responding.
Precisely. And underlying all these phases, solid, liquid, gas, plasma, is the fact that everything is made of these incredibly tiny things, molecules and atoms. For ages, scientists wondered, how do you even begin to measure or count something you can't possibly see, especially when there are just billions and billions of them in the tiniest speck?
Yeah, the scale is hard to imagine.
Right. It led to some really clever ideas, building on work from people like Dalton, who first really pushed the idea of atoms, and Avogadro, who helped figure out how to relate gas volumes to the number of particles. So let's unpack some key vocabulary that helps us bridge that gap between the microscopic world and the world we can actually measure. These are like our tools for counting the uncountable. First up, the mole. Okay, don't let the name scare you. It's not the furry animal. Think of a dozen. What does a dozen mean? 12 something, right? A dozen eggs, a dozen donuts. Well, a mole is kind of like that. But for atoms and molecules, it's a specific amount of substance. It represents a specific, incredibly huge number of particles. The official definition is tied to carbon-12. It's the amount of substance that has the same number of particles as there are atoms, in exactly 0.012 kilograms of carbon-12.
Okay, why carbon-12 specifically?
Good question. Because it's super stable and common, it gives scientists a reliable, universal benchmark to work from. The mole is the concept that lets us connect the atomic scale to lab measurements. It's how chemists and physicists can actually do calculations and predict reactions. Then there's the atomic mass unit, usually just written as U. If you want to talk about the mass of one single atom, using kilograms is awkward. Numbers are unbelievably tiny.
Like 10 to the minus 20-something kilograms.
Exactly, so we use U. One atomic mass unit is defined as 1/12 the mass of a single carbon-12 atom. It's roughly the mass of a proton or neutron. And yeah, its value in kilograms is tiny, about 1.66 times 10 to the power of minus 27 kilograms. It just gives us a more manageable number for atomic scale masses. Building on the mole, we have molar mass. This one's pretty straightforward. It's just the mass of 1 mole of a substance. Usually we measure it in kilograms per mole or sometimes grams per mole.
So it tells you how much a mole's worth of something weighs.
You got it. Like, how many grams of water do you need to have 1 mole of H2O molecules? And similarly, there's molar volume, Vm, which is the volume that 1 mole of a substance takes up, usually cubic meters per mole.
Connecting the invisible count to measurable size and weight makes sense.
Exactly. They make the mole concept practical. And finally, the number itself, the actual number of particles in 1 mole. That's the Avogadro constant in A. And it is 6.02 times 10 to the power of 23 particles per mole.
Wow. Okay, 6.02 times 10 to the 23rd. That number is just staggering. It's almost impossible to actually picture.
It really is.
I read somewhere, like, if you had Avogadro's number of marshmallows, they'd cover the entire United States to a depth of over 600 miles.
I haven't heard that one. Or grains of sand covering the whole Earth miles deep. It just shows how incredibly numerous atoms and molecules are, even in a tiny sample of stuff.
Which is exactly why we need the mole in Avogadro's number to even talk about them sensibly.
Absolutely. And like you said, sometimes elements are just single atoms floating around like neon in a sign. But mostly what we encounter are molecules, atoms bonded together. The oxygen we breathe isn't just O atoms, it's O2 molecules. 2 oxygen atoms stuck together. Okay, so that leads us right into the core question. If all these atoms and molecules are constantly moving, especially in liquids and gases, and we know there are so many of them, why doesn't everything just fly apart? Why do solids hold their shape? Why do liquids stick together?
The invisible glue.
Exactly. It comes down to the invisible forces acting between these particles. It's like this constant battle, a tug of war inside all matter. On one side, you have kinetic energy, the energy of motion, that's always trying to make particles spread out, fly apart.
Which increases with temperature, right?
Right. Heat things up, particles move faster, more likely to break free. That's phase changes like boiling water. But on the other side, there are forces that attract particles to each other, pulling them together.
So motion trying to separate them, attraction trying to hold them together. So are you saying every atom is sort of constantly being pulled towards its neighbors, but also trying to push away or fly off because of its own energy, like a push me, pull you situation?
That's a great way to put it. Let's break down that push and pull. There's a natural attraction between atoms and molecules. Think of them like tiny magnets, wanting to get close. That's what keeps them generally near each other in solids and liquids. But if you get too close, things change. There are electron clouds, those fuzzy outer regions with the electrons start to overlap, and electrons being negatively charged repel each other strongly.
Like trying to push the north poles of 2 magnets together.
Exactly. It creates this really strong repulsive force pushing them apart. That's why solids and liquids are so hard to compress. You're fighting against that electron cloud repulsion. Now, the really cool part is that there's a sort of sweet spot distance, a point where the attractive force pulling them together and the repulsive force pushing them apart perfectly balance out.
Equilibrium.
Precisely. We call it the equilibrium distance, R0. At this specific distance, the total net force on an atom is 0. If it drifts further away, attraction pulls it back. If it gets pushed closer, repulsion shoves it away.
So they're always trying to get back to that ideal spacing?
Yes.
Yes.
They're held in this dynamic balance, constantly vibrating around that equilibrium point. Your textbook has a great analogy for this. Imagine 2 balls connected by a spring lying on a table.
Okay.
And the spring is just relaxed at its natural length. The balls are happy. That's the equilibrium. If you push them together, the spring compresses and pushes back out, right? Repulsion. If you pull them apart, the spring stretches and pulls them back in. Attraction. Atoms and molecules interact in a very similar way, always trying to maintain that balanced distance or 0. Okay, so this attraction we keep talking about, the thing holding atoms together near that equilibrium distance, that's what we call a bond. And these bonds, these forces, are fundamentally electrical in nature. It's all about electrons. And there are a few main ways atoms can form these bonds. First, there's ionic bonding. This is kind of like a transfer deal. One atom literally gives one or more of its electrons to another atom.
An electron handover.
Totally. The atom that loses electrons becomes positively charged, a patient. The atom that gains electrons becomes negatively charged, an anion. The classic example is table salt, sodium chloride, and ACl. Sodium has one electron in its outer shell it wants to get rid of. Chlorine needs one more to complete its shell.
So sodium gives, chlorine takes.
Bingo. Sodium becomes NOT plus chlorine becomes Cl. And what do opposite charges do?
They attract very strongly.
You got it. They snap together because of that strong electrostatic attraction, forming a rigid crystal lattice. That's why salt is a hard, brittle crystal. Okay, second type, covalent bonding. Here, instead of transferring electrons, atoms share them.
Teamwork?
Kind of. They share electrons so that they can both effectively complete their outer electron shells. This sharing creates a very strong link holding them together. Think about the oxygen molecule, O2 again. Each oxygen atom needs 2 more electrons, so 2 oxygen atoms get together and each shares 2 of its electrons with the other. That forms a double bond.
A shared pool of electrons holding them together.
Exactly. This is super common. It's the main type of bond in organic molecules, like everything that makes you, the plastics in your phone, wood, sugar. And it's responsible for the strength of things like diamond, which is just carbon atoms covalently bonded in a super strong network. And the third main type, which is pretty unique, is metallic bonding. This happens, unsurprisingly, in metals. Here, the outermost electrons of the metal atoms don't really belong to any single atom anymore. They become delocalized. They form this kind of sea of electrons that can move freely throughout the entire piece of metal.
A sea? Okay, so the electrons are just swimming around.
Pretty much. And the metal atoms themselves, having lost those outer electrons to the sea, become positive ions. These positive ions are then held in a fixed lattice structure by their attraction to this surrounding mobile sea of negative electrons.
Okay. The positive atoms are anchored by the negative sea flowing around them.
Exactly. And this structure explains so much about metals, why they conduct electricity. Those free electrons in the sea can easily move and carry charge. Why they're shiny. The electron sea interacts with light in a specific way. Why they're malleable, bendable. The atoms can slide past each other, but the electron sea just flows around them, keeping the whole thing bonded.
That's fascinating. So whether it's giving and taking, sharing, or this kind of communal electron sea, it always comes back to electrical forces. That fundamental attraction and repulsion based on charge is what holds literally everything together, determining if something is hard like salt, shareable like oxygen, or conductive like copper.
It really is the basis for almost all material properties.
Yeah.
And knowing these principles is powerful. Physicists can actually use this knowledge, combined with things like molar mass and density and Avogadro's number, to estimate the average distance between atoms in a substance.
Without actually seeing them.
Without seeing them. By figuring out the volume one mole takes up and knowing how many atoms are in a mole, you can calculate the effective volume per atom and from that, estimate their average spacing. It's like having a microscopic ruler built from macroscopic measurements. Pretty neat stuff.
Okay, so let's do a quick check on that force idea. Thinking about that spring analogy and the equilibrium distance R0, if you were to push 2 atoms closer than R, what's the main force doing? Pushing or pulling?
Closer means they're too close, so repulsion takes over. They push apart.
Got it. And if they're pulled a bit further apart than R?
Then the attraction would win, pulling them back together.
Sure.
Trying to get back to that sweet spot.
Exactly. It's that constant balancing act that defines the structure and properties of matter.
Wow, okay. We covered a lot of ground today, diving deep into the world of atoms and forces. Let's do a quick recap. We started with the phases of matter solids, liquids, gases, and that super common, super hot plasma that makes up stars and most of the universe. We looked at why they're different based on particle arrangement and motion. Then we tackled how we actually count and measure these tiny particles, using concepts like the mole, the atomic mass unit, molar mass, molar volume, and that enormous Avogadro constant. We uncovered the crucial interplay of forces, the kinetic energy pushing particles apart and the attractive forces pulling them together, finding that sweet spot at the equilibrium distance. And finally, we explored the main ways atoms bond: ionic, transferring electrons, covalent, sharing electrons, and metallic, that unique sea of electrons. So here's a question for you to think about, based on everything we discussed. Why does it take energy like heat from a stove to melt ice into water or boil water into steam? Consider those forces we talked about. What are you actually overcoming when you add that energy? Stay in contact with your physics teacher. Stay creative.